Just gonna start the recording. Okay, so today basically the plan for us is we're gonna
Your
go
screen is
through.
not sharing.
Sorry, can you repeat that?
Your screen, no, your screen share is not on.
Oh, gotcha. Thank you. All right, let me know if you can see it.
Yeah.
Yep,
Awesome.
it's good.
Thank you. Okay, so first thing is we're gonna go through. I guess the lesson plan for today is we're gonna go through massive materials, assemblies, basic and advanced mating, and reference geometry. So we're basically going to continue off of what we were doing last time. So we should have the gear sprocket from last time. I think that's what it's called. I'm not sure. That's what somebody said last time. We're going to work on making the pedal and maybe looking for the central shaft as well for the bike frame, and we'll see how far we get from there. First off, before we do that though, I'm just letting you guys know, especially the ones who are in person, we do have something else coming up potentially next week. We have a CAD project that was given to me by one of the other leads to do. So as part of this group of people working on SolidWorks, occasionally we're going to get actual practical work to do for the team as we go. And there's one fairly simple CAD project that we've been given to take a look at, and that is related to the American competition. We have a system that we need to develop to release packages from a drone in a controlled manner, and we need some mechanical design work done for that. So that's something we're going to take a look at for probably about half an hour in next week's session, just so you guys are aware.
Our
And then so for today, we're going to go through, we're just going to start off by making a part just to kind of refresh our knowledge. And then we'll go through some of those practices I mentioned before. Okay. You guys can see this when I pull it up, right?
Yep.
Okay. So last time we finished this part, the little arm here, our SRAM arm. Yes, this is getting recorded. And so we finished the arm here, so we're going to move on to doing the pedal. We're going to work on this central shaft here, and time permitting, we'll do this front gear wheel as well. Okay. So first thing we're going to do is let's take a look at the pedal. We're going to estimate, or I guess we'll pull from the previous part we made, the diameter of the inside of this, of the inside hole here. Okay. So first thing we're going to do is open up our old drawing. Let's take a look. Sorry, I forgot where I put this. 1 second. Okay, I have it here. So we're going to open the pedal arm. And so basically there's two ways we can go about doing this. There's kind of one simple method, which is one you would typically use, which I'll show, which is we just measure that dimension to make sure the part that we make will properly mate with this component, okay? So if we take a look at this, we're just going to measure this hole. So we're going to go to evaluate and measure. We're just going to click on the inside loop here. We can see this is 12 millimeters. 12 millimeters. So I'm going to save that in the chat. So the outer diameter there is going to be 12 millimeters. So there's two ways we can do this. We can create a new part. Well, we're going to create a new part either way. So you can go ahead and do that. That'll open a separate part document open. And there's two ways we can go about doing this. Way number one is for us to just put in that 12 millimeter dimension into the new part. So basically what that would look like is you basically just start a sketch and you just go ahead and throw a shaft model in and set it to 12 millimeters. Okay, we're going to exit out of this real quick, go back to our other part, take a look at the width dimension here. So we're going to measure again. So evaluate, measure, click on the front face, click on the back face, and we're going to look for the black distance. Sorry, the normal distance, sorry. So this is purple. which is going to be 12 millimeters as well. Okay. Go back to our old drawing, and we can extrude that by 12. Okay. This is a simple method, and this works more so for aesthetic CADs, less so functional CADs. The reason why this doesn't really work very well is for two reasons. One, it's missing a bearing, which is something we're going to have to add. So we're going to have to look for a bearing part to put in between the gear arm and the pedal. The other reason why this doesn't work is if you were, for example, to change that gear arm for a different type, the size of this of the shaft would not update, right? So instead of doing this, something that I'm going to recommend we do is actually import the other part. So this is practice we can do. So I think it's insert part, right? So up in the top bar, I'm just going to pin this as well. So insert part, and we're just going to go and open the pedal arm in this drawing. Yeah, so that's fine. And what we're going to do here is base the new part off of this part's dimensions, okay? So what we're going to do is we're going to go and grab this inner tube here. Let's do a 3D sketch. Okay, so just going to go under sketch, create a 3D sketch, select this inner part, and click convert entities. Sorry, you might have to click the outer rings. Okay, and so that basically creates the ring on either side that we are concerned with. Just gonna take a quick Google search here on MasterCar. I'm gonna take a look for standardized bearings, which are here. So we're going to look for housing diameter, I believe. There should be outer diameter. Actually, don't sell any that are small enough for this purpose. Bearings. Interesting. MasterCard doesn't sell them. Typically, MasterCard is good because they offer all of the part files for their different bearings and parts and stuff like that. In this case, they unfortunately don't, which is okay. We're going to go ahead and go back to this. Okay. So what we're going to do is we're actually, now that we have this, we're going to exit out of the sketch. So we have our reference dimension. And what we're going to do, actually, sorry, before we do that, go back into the sketch. Before we do that, we're actually just going to smart dimension this side. So make sure you're doing the side that the pedal would be on. We're going to smart dimension this side. Okay, hold on. It's being finicky. Okay, cool. So you actually don't have to force that dimension, which is good. So basically what I did there is I took the pedal that we made last week. I've imported that into our current drawing, or into our current part, sorry. I created a 3D sketch to map the outside of the hole, the outer edge. And then basically I created another sketch just to import the single loop that we want into our drawing. And so now this outer ring here is going to match the dimension of the pedal arm that we made last week. And if we make any changes to that pedal arm, it's also going to reflect in this drawing as well. So in this case, this is not something we have to worry too much about because we won't be changing the size of that arm. But for future CADs that we do on this team, it may be something we have to be concerned with. So we always want to make sure that the parts we make are built relative to the other parts in our systems. Okay. So we're just going to go ahead and take the extrusion tool. See if we can extrude this. It might be difficult to do in a 3D sketch. Yeah. Okay. Let's see if we can do this using some reference geometry. So what we're going to do is we're going to start working with a little bit of reference geometry. So this is basically non-functional parts that you can import into CAD that allow you to create references for future geometries. So for example, I can create a plane. I know that this ring here is going to be consistent, at least in its location and its direction, right? So I can click on this and I can create a plane that's defined at this location. So this is a separate plane that's separate from our origin, separate from our main reference frame that allows us to build different reference geometries based off of. Okay, so that's one. That's how you do a reference plane. Now there's a few ways you can do that. You can do it based off of points. You can do it based off of lines. There's a bunch of different ways you can create that, and you can mess around with that quite a lot. You can make axes. So for example, I'm going to make an axis between this point and that point. Okay, so 2 points are enough to define a line, as we talked about in the first meeting. This line then can be extended into an axis. Okay. We can do a point, so we can make the center point there reference, center point there reference. I'll do one at a time. It's okay. We can enter an entire coordinate system. So for example, if we needed to do calculations based off of, moment of inertia or something around some specific point, we could basically define, that as a coordinate system. And you can see it's taking our, x-axis as the front of that coordinate system there. Okay. So these are something you can do. It can be quite helpful as well. You can do a lot of measurements based off of that. When we start getting into more complicated CAD down the line, those are going to be tools that are very helpful. All right, let's see if we can do an extrude now. So we're going to take this plane and we're going to extrude this. Okay, and I'm just going to go ahead before we do that and check our reference design. I'm going to take a look at this model here and see where the shaft needs to go to. So if we take a look at it here, we're going to omit a few of these details. There is a bearing here and there is a shaft that comes out of it, and there's a few different ridges in this. Just for the sake of all of our time, we're going to omit some of those details and just make this a straight shaft coming out of this. As far as the CAD model is concerned, that is effective enough. When we do our CADs for the team, please make sure that you don't omit details like this, because having a bearing there and not having a bearing there is a very big functional difference. But for the sake of learning CAD, it's not particularly relevant. Okay, so we're going to take a look at this from the top here. We know this is 12 millimeters. This is approximately double that. So let's say 25. We're going to extrude that out, and then we're going to build the rest of our pedal based off of that geometry. Okay. So while we're here, I'm just going to go ahead and grab a screenshot of this and do the same method we looked at last week of creating some reference dimensions based off of a drawing. Okay, and then we're going to go to leaf. Open up that image. Okay, and we know that this is going to be approximately 25 millimeters. So we can take a rough measurement for, let's say, this size here, which is going to be the total size of the pedal, by this size. we'll figure out how far this needs to come in. So we'll say from here to around there is our indent on that side. And then check our indent on this side, 10.21. Grab a few dimensions here, 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 here. I think that mostly covers it. I'll just grab a screenshot of this and put it in the chat so that you guys can use that as reference. Okay, go back into our CAD software. I set this as 25. Extrude that out. Okay, next thing we're going to do is take a look at where our reference frames are. So we have top plane, right plane, and front plane. None of these are particularly useful for us. What we really want to do is have kind of a mid-plane created from this, this model here, okay? So what we're going to do is we want a plane that is flat kind of through this point here in the center, and then that kind of bisects our shaft, right? So what we're going to do is we're going to create a reference geometry in a plane, right? So there's a few different ways we could define this. For example, one way is we could do a 3D sketch, and we could create a second axis that goes from this point to a horizontal point out this way, and we can create a plane that way. One way that I think is a little bit better is to take a look at the main reference frames, the reference planes that we have, these main top, front, and right. Figure out which one matches. So for us, it's the top plane. That's kind of what we want, right? And so what we're going to do is define the plane based off of the initial reference top plane and then one additional point. So we're going to use this axis 1 point, okay? So we know, because that axis 1 point is the center of our shaft, that this plane here will be parallel to this top plane, which is our main reference frame. Make sure basically whatever part we make is kind of in line with that reference, and then it bisects the shaft through the middle, okay? I'm just going to hit OK. So now we have this center plane to draw on, right? And we can draw on this plane anywhere, but just for the sake of making it a little bit nicer to look at, I will extend it out a little bit. But you can imagine this plane, as far as the CAD software is concerned, is infinite. So it doesn't restrict you to drawing on it in any way. Okay? Right, so now that we have that opened, a good thing we can do is convert the top edge here of our shaft onto our plane here. So we have a line now that is the center of, or sorry, along the top of our shaft. What we're going to do is define a reference point in the center. So what I'm going to intentionally do is put it off to the side here. Click on it, and then hold Control, and then click on this main line. This is going to allow me to create a relationship. So similar to what we were looking at last week, I want to force this point to always be in the center of this line. And so since I know it's on this plane, which bisects the center of our shaft, I know that this line, this dot, if it's in the middle of this line, it's going to be the center point of this shaft, okay? So you can hit midpoint, and we see this is here, and I know the height of this will be directly in the middle of the shaft, okay? Keep in mind, again, to always check, make sure your drawings are fully defined down in the bottom right corner, okay? All right, so I'm just going to go ahead and take a look over at our reference drawing again. So first thing we want to do is start off with a rough sketch of what this face is going to look like. We'll probably put these holes in first, and then we're going to extrude into the third dimension, and then we'll worry about doing some extra details afterwards, okay? While we're at it, I'm just going to save this document as well. So following the same naming convention we used before, this is going to be part 02, and it's going to be puddle. Okay. I'm going to open up this corner or the rectangle menu, and I'm going to take a look for a rectangle that matches what I'd like. So probably 3-point center rectangle is what I'm looking for. So I want something that looks like that. So this should be defined now. It should stay on. No, okay. I have to force that definition. So basically just create a rectangle. It's not too big of a deal which one you create. And we're just going to make these two lines collinear to make sure that the pedal stays in line with the shaft. Okay. We're going to set this point down here to be vertical with that point. Right, so now we have our location defined, right, left and right location. I'm going to take a look at our drawing here. And extend this out a little bit. So I know that this dimension is going to be 75. I'm going to round the measurements a little bit just to make it a little bit cleaner. I know that the full dimension from here to here is 75 as well. However, we have that bend to worry about. So what we're going to do instead is subtract the 6 millimeters from our indent off of that and make this 69. Okay. What I'm going to do is on this right side here, I'm going to extend this out. Make sure that this line is vertical. You can tell by that little relation there that the horizontal or vertical line. And then just connect it back down to the center right there. Okay. We know this needs to be 6 millimeters to add up to 75. So we can fill that dimension in, and this corner should be fully defined. Yep. We can see our entire sketch now at this point is fully defined, so you should be able to click on different parts of your drawing and it should not be moving anywhere. Okay, that's step one. Next thing we're going to do, let's create a reference line down the center. There's no point in wasting time in trying to mirror this on both sides by hand. We're going to focus on doing the right side and then we're going to mirror it over to the left later. So I'm just going to set the center line as for construction on the left here, and I'm going to set it as infinite length. Okay. This just makes it a little bit easier to see, and it won't affect any of our extrusions and stuff like that. It'll make it easier to deal with these things later. Okay, and I'm going to look down on the bottom side here, and it looks like the indent on the top on this right side is a little bit bigger than the one at the back. So we're going to go ahead and do that as well. We're going to set it from here to there. Make sure that this is 7. Okay. I can see now that I'm missing a dimension, which is the distance from this point to the center. I'm just going to go ahead and grab that dimension as well. So I'm going to go from here to about there. It's about 23, so let's round that up to 24. So we know the distance from both sides needs to be 24. So I'm just going to half that and make it 12 for this side. Okay. I did notice that my line here shifted. So this is not defined properly. So we're just going to go ahead and make sure that it goes through this point. Okay. Make sure you always drag your reference geometries and stuff and make sure they don't move. It's very important. Okay, so we're back to being fully defined, which is good. What else do we have to do? We have an inner cutout here, and then we have an inner cutout here as well. So let's tackle this top one first. So the cutout is supposed to look a little something like this. So we have a line going across here. We'll make sure that is vertical. It's going to come out to here. It's going to go across this way. Make sure that's vertical as well. And then it's going to come back to there. Okay. And then on this side, we're looking at something that looks a little bit like this. So there'll be a line here. Sorry, that is incorrect. This one actually crosses the center, so to make sure it's symmetrical, we're going to pull it out from here. It's going to go out to around here, and then it's going to come back down that way. Okay, so first thing is these two lines should be parallel. So we're going to set those parallel to each other. These two are vertical, so those should be in line with this line. And then this bottom one and this one should be parallel. And then this line and this line should be parallel. Okay, and we can just shift these over so they look a little better. Okay, we can start to add a few of these dimensions in. I know these inner two kind of lines that come out, these sections here are going to be around 6 millimeters. I'm just going to go ahead and add those dimensions in. Six. This one is a little bit bigger. This one is closer to 10, so let's do 10. Okay. We're just going to make sure we pull this in a little bit. So you know this one is 10 as well. The size of this middle arm, so we're going to set this equal to 5 for this side. Oops. Sorry, that's the incorrect dimension. From here to the center should be 5. We know this outside is supposed to be about 15, so we're going to set that to 15. Okay. So at this point, what are we missing? We're missing this whole section, so this should still be able to move a little bit, and then this top line is not defined. Okay. So we need 2 more dimensions. We're going to go into here. We're going to grab this line here. So that's about 45, let's say. We need this dimension, which is about 15. And then we need this dimension, which is about 20. I'll go ahead and grab another screenshot of that. So this distance from the edge point to the center line is going to be 20. The distance from here to here will be 15. And then this distance here is going to be 45. Okay, so we can see that we're hitting our full definition, which means if I add any more dimensions, we are going to be over-defined, which we don't want. So we can see here this top one is around 48, which is okay. It's a little bit more than our dimension predicts, but you can see from the edges here that there is some fillets on the inside. So if we estimate from around there to around there, we should see that's a little bit closer to 48. Still closer to 45, but our geometry is close enough at this point to say I think this is probably pretty close to the real dimensions, and we can do a little bit more shaving using fillets and stuff like that once this is extruded. Okay, so next thing we're gonna do is, now that we've done one side here, we're gonna mirror that to the other side. So I'm gonna take mirror entities up here. Okay, so it's in Sketch, mirror entities. We're gonna mirror about the center axes, all right, the center reference line we've created, and we're gonna select all of the entities that we want to mirror over. Okay. So what we should see is virtually a carbon copy of everything that we had on the right side onto the left side. Okay. So now we see this is all mirrored. We can check again, make sure we're fully defined, which we are. I'm just going to go ahead and hit the rebuild icon. So this little stoplight looking icon at the top, just to make sure all my dimensions and stuff are accurate, and I'm going to come back into my sketch. Okay, everything's still fully defined, everything looks good, so we're going to go ahead and pull this into the third dimension again. So we're going to go to our extrude tool, and we're just going to go ahead and select all of those objects here. I'm going to pull into a better view to make sure what we're doing kind of makes sense. Okay, and we're going to do midplane. We want midplane because we want to make sure that the pedal extrudes equally above and below the shaft. Just this is something that should be intuitive to us, right? I know that the dimension for the height of this is something we can find as well, so we're going to go and take a look at that. Okay, so we know the rough height will be about that much. Do we have any reference? We do. So we can see that the shaft size and the pedal size are very close to the same. So we know the shaft size is 12. So let's make this 14. We can do a little bit shaving off as well afterwards. So we'll make this 14. Okay, and it looks vaguely pedal shaped at this point, which is good. We know we're kind of on the right track here. Okay, so first thing we can see is still looks a little bit too big, doesn't it? Just gonna double check my my dimensioning on this. So from here to here is about 24.2. Okay, if we go to our pedal, this probably is a little too small. What is going on with this tool? Point to point, so we want to click here to here. Okay. I'm not quite sure what's going on here, to be honest with you, but that's okay. We're just going to do some shaving, and it should line up pretty close. All the dimensions were inputted pretty correctly, so once we do the shaving, hopefully look a little bit closer to our pedal. So what I'm going to do first is start with the outside edges around here. There's a few things we have to do. So on our pedal, we can see that we have these kind of chamfers around the edges here. So you can see these are, these angled cuts here. I don't know exactly what angle that is, so we're just going to do an estimate. And so we're going to do that around about this. So from this face and then about halfway up this face. And then that side, there's a bit of a cut down as well. Actually, looking at it now, I think we have to do a separate kind of diagonal cut here. So let's do that. We're going to do that diagonal cut first. Okay. This face here should be perpendicular, which it looks like it is. So we're going to use this face as our sketch plane. Okay. We're just going to click on these three rectangles and convert entities. Okay, so we can pull that. You can see here, if it wasn't clear what we were doing earlier, that we're converting, that basically projecting these faces onto our current plane, right? And we're just going to kind of draw our curve, our S curve. Oops. Our kind of S curve like this onto it. Just going to do a simple one here. Something like that. It's pretty small. It's pretty small, so we'll set it around there. And I'm just going to grab our tool here, and I'll say 5 millimeters. Should be fine. Okay, and so that should be defined pretty well. And we're gonna just go ahead and mirror that onto the bottom as well. So what I'm gonna do is grab a line. Actually, sorry, this one we're gonna have to rotate around the center. So what we're going to do here is we're going to create a line for reference across the center. Okay, so what we're going to do is make sure we have midpoint on both sides. So you can hover over and make sure you connect to the midpoint on both sides, so this shouldn't be able to move up and down. Okay, we're going to grab a point and make sure this is midpoint in the center as well. You can see that there's a little point in the middle of a line there. Make sure you can drag it and it doesn't move as well. Okay, we're going to grab our sketch fillet tool. So the same way that we have our fillet tool, our general fillet tool that we can use on bodies, so on these built shapes, we can also use these on sketches as well. Okay. Also just going to make these for construction as well. Okay, they won't let me do that. That's fine. We're going to go ahead and grab our sketch fillet tool, which is right here in the bottom right, and make sure we just select this corner. Let's see. Gonna let me do this. Yeah. So select the two edges there, and so we can create this fillet pattern here. I think we can probably go a little bigger here, so like 2.5. Probably closer to what we're looking at. Okay. And we're just gonna go ahead and rotate that. So what we can do here is we can do a circular sketch pattern. So I think last week we took a quick look at linear sketch patterns. So what we're going to do is we're going to use a circular sketch pattern. So this works very similar to the mirror tool that we looked at before. But instead of mirroring something about one central axis, what we're going to do is rotate it. Okay. So what we're going to do is we're going to select that center point as our reference. Okay. And then the entities to pattern field down here, we're just going to make sure we click these. I think there's a little line there. Make sure you don't forget that as well. Okay, sometimes SolidWorks doesn't like to do exactly what you ask it to. So what I'm going to try to do is use that axis instead. No? Okay. Let's try doing it around the axis instead of around the point. Okay, let's try around the axes. It really does not want to cooperate today. Okay. Okay, so what we're going to do instead is we're going to actually do the cut, and then we're going to do that pattern afterwards in the body format. This is something that, honestly, I don't know what is going on with SolidWorks today, but it's kind of a pretty common bug that happens with SolidWorks every once in a while, that you have issues doing something in drawing. So we're just going to go ahead and do it a different way. So we're going to do an extruded cut. Okay, make sure we grab all three sections here. And we're just going to blind through all both. Okay, so that's going to cut to the top here. I'm just going to double check. So we can see that it is cutting through a little bit of our shaft as well. So we're going to have to change the way that we manage this a little bit. So let's see if we can cut up to surface. Does that work? No, it does not. Okay. So there's two ways we can go about this. Is we can go change how we extruded the original design, or we can do kind of the quick fix method, which is what we're going to do for the sake of time today, which is we're going to cut through our shaft and then just fix it after. I highly recommend you don't do this when you go through and do your own CADs, but for the sake of time today and the fact that this part are not going to be manufactured, that should be just fine. Okay, so we can see that we have that kind of cut that we were looking for in the pedal. What we're going to go ahead and do now is rotate that. So instead of a linear pattern here, we're going to go for a circular pattern. So you can see there's a few other different types of patterns. So for example, there's table-driven patterns, there's variable patterns. These are things that we kind of talked about a little bit in our first session where we talked about equation-driven CAD. So this is things you can do. You can use different tools to generate tables and then use those tables to generate parts. We use methods like this when we start working with airfoils, which we'll see in a future session. Okay, so I'm going to grab the circular pattern. We're going to rotate around our central axis. And we're going to try to grab this cut feature. Okay. Okay, so now if we set this equal to equal spacing and we have 2 of them, it should you should see that this kind of mirrors, and you can take a second to convince yourself that this is accurate geometry. We are cutting through the top and we're cutting through the bottom in the same way, and we're rotating that about the central axis through our shaft. Make sure you're on equal spacing, that this says 360 degrees. If it doesn't, you can see that even a little bit off and you start getting some weird angles and stuff like that, right? So let's not do that. Instance spacing here, you can set different instances. So for example, if we wanted to do a pattern of cuts, we can start setting things like these. You can see that we have these kind of interesting patterns that come up. For us, most of the time we're just going to be worrying about equal spacing. We're gonna hit OK. All right, and we should see that that successfully cuts through everything like we wanted it to, which is good. Next thing we're going to do is look at the chamfers. So we want to grab this side and this side here, and we're going to do a chamfer. All right, so you can see we're starting to get that edge we were looking for. But instead of doing a symmetrical distance chamfer, what we're going to do is we're going to do a distance chamfer, okay? So what this is going to let us do, we want it to be asymmetrical. This is going to let us choose basically the angle by estimating the different sides, okay? So I'm going to zoom in here. I know the total height of this from here to here is 14. So this length here, let's pull this into, be a little more precise, let's pull this into a leaf. All right, just refresh the page. I'm going to choose petal number 2. Okay, I know that my full dimension here is 14. Okay, so this side here is going to be about 9.5. So let's say if we go from here to here, it should be about 9, right? Yeah, so we'll use 9 as our top. So 14 minus 9 is 5. So we're going to look at, I think it's this one. Yep, so 5, and then we'll take a look up here. How far is this distance? Oops. It's about 7, let's say. Okay. So we should see that kind of pattern go around. We're going to hit OK. And we can see that's starting to look a lot like the kind of petal shape we're going for. Okay, so I'm going to go ahead and now mirror this to the other side as well. So using the same method as before, we're going to do a circular pattern. We're going to select that central axis as our rotation axis, make sure we're on equal spacing, and we're going to select those chamfer features. Okay, and hit OK. Chamfer items are no longer in the model. The features items. Interesting. I have not seen that error before. Do let me know, guys, if you run into any errors, by the way, as you're going. Take a look at them together. Okay, this doesn't want to work, so I'm just going to go ahead and just repeat it on the opposing side. Okay, so I'm going to make sure we do distance, asymmetric. We can see the same dimensions were pulled in. Oh, so I see. For some reason, it's taking all the way to there, which is asymmetrical from the other side, even though we have the same selection. Cool. That's very strange. Okay. Mostly we're doing this for aesthetic purposes, so for this, I'm going to say it's okay. In future, I would spend some time, definitely if I was doing this for a more functional CAD, I would spend the time to figure out why that's happening, but you guys can maybe take a look at that on your own and see if you can figure out exactly why that is happening. Okay. Next, we're just going to smooth out the object a little bit, so I'm going to grab the far edges here. Let them, let's do, say, a 5mm, the outside. Can see there's one more feature here we're missing, so I'm just going to open up a sketch here, and we're going to convert these lines. I'm just going to actually extend these lines out a little bit. Okay, so I'm just going to do this by making these collinear. It's going to give me a little bit of room to play with. What we're going to do right now is basically cut out this little section here at the top where the 3 screws go. There's a little divot down, so we're just going to cut that in. Make sure this and this are parallel. And then the last dimension should be this distance here, which we're, let's say is 5. That looks a little too big. Hold on. Say it's 3. Okay. This should be fully defined. Double check by always pulling on the corners. Seems fine. Okay, while I'm doing this, I'm also going to go ahead and add in my sketch fillets. So we're going to do this corner and this corner. Just going to double check on this side. There's a little bit of a gap there, which I don't like. So I'm going to make this a little smaller, let's say 2. Just to make sure that we're within our bounds here. Yep. And hit OK. And so we're just going to cut out this chunk here. Extrude to cut. Click here. Go ahead and set this as, say, 2mm down, 3mm down. Okay, so we can see there's some kind of broken geometry here. So there's some leftover artifact here we don't want. I'm going to go ahead and open our sketch back up. See what's going on here. Okay, very strange. Okay, I'm going to go ahead and delete these. I'm going to do this afterwards. Filleting tool in SOLIDWORKS is being a little finicky right now. That's okay. Once again, make sure these are collinear. Collinear. Make sure these are parallel. Set this to 3mm. Okay, we're going to back out. And we're going to go ahead and do our cut. Which, let's see if that works. Yep, that works. We can also see this time there's still kind of some kind of weird artifact there. I'm not quite sure why that is happening. Oh, I see. It's because this face is okay. All right, so this is actually a very good, very good teachable moment. So I've made a very common error here. So what I've done here, I don't know if any of you guys caught this, but we cut an angled face into this part. And so when we created this drawing on this face, it's actually creating an angled cut into the drawing, right? So there's actually two ways we can easily fix this. One is we can project this, drawing that we have onto a plane that is, in fact, perpendicular to the cut we're trying to make. Or we can actually change the direction of the cut itself. So if we go ahead and go to our cut and edit feature, we should be able to, I think we should be able to select a line like this, which should correct the cut to make sure, there we go, that it's in line with that. So basically what I did there is I just selected a line here that I knew is in the correct direction, and that is perpendicular to the cut that we're trying to make. And what that did is it just shifted the cut over to make sure it's in line with our reference geometry and not this face here. Okay. So let's take another crack at seeing if we can rotate that around. But something tells me it's not going to work again. Okay, this time it wants to work, which is nice. So I'm just going to go ahead and add a bunch more fillets here. Okay, I'm just going to go ahead and maybe grab inside there, inside there, inside there, 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 and there. And set this to maybe 2. Looks about right. Okay, and then we're going to set the insides here, so these 4. These ones look a little bit bigger, so maybe let's do 5. Then we have this one and this one. Okay, and this one looks significantly larger. Let's maybe do 15. Okay, we have 15, and then what else? It looks like the inside there is good. We have that. Okay, there is one more feature here. There's a chamfer around this edge as well. We're just going to go ahead and set that. This one I'll leave as asymmetrical and do 1 millimeter. I think that looks pretty close to what we're going for. It's not really anything else. I am just going to smooth out some of these edges as well, just so it looks a little bit better when we start doing our render later on. I believe we're also going to be touching renders towards the end of this as well. So I'm just going to grab this instead of very small, let's say 0.5 millimeter fillets, and we're basically just going to grab all around the outer face, smooth these up a bit. Just going to make sure that our preview stays lit all the time when we're doing this. Okay, we can see that all of those are staying lit, which is good. Okay, so we can do that on the top face. See if we can do this as well. Cool. And if we go ahead and pop out of our shaded edges view, we're going to pop into just shaded. you can see the edges of this are much cleaner, and they're going to look a lot more like the machined pedal part that we're kind of looking for. Okay. Now to save the time of having to go and do that on the other side again, pop back into our shaded view. What I'm going to do is just rotate that around the center axis as well. Let me see. Actually, because of our earlier asymmetry, I'm going to have to go ahead and do these by hand. Typically, you would just rotate this around the center axis again to basically skip going through these steps, but that's okay. Yep, thank you for coming. Okay, we're just going to finish up these. Okay, so you can see that's our pedal mostly finished. Last thing I'm going to do now is go ahead and create another sketch here. And I'm just going to fix that problem we had before. I'm going to re-extrude this up until the face there. So I'm going to use up to surface here just to make sure it pairs up to that surface that we have. I hit OK. We should see that there's a little bit of a cut there, which is okay. That's where our kind of pedal starts. So I'm just going to go ahead and grab that at the top and bottom. Make that look a little cleaner. Adding a fillet in. Leave it at 0.5. That's okay. I'll just make that a little bit smoother. Okay. That's going to be our finished pedal for right now. We can go ahead and save that. I'm going to go ahead and throw on a kind of bronze looking material as well, just to make sure it looks like what we are going for. So this looks like a polished bronzy kind of color. So we'll do something like that. It's maybe a little too bright. Maybe more of a brushed. Yeah, that's what we're looking for. Okay. I'm going to go ahead and save that. We're not going to put in the screws and stuff like that because it's a level of detail that we don't really need in a functional CAD. It's kind of outside the scope of the tutorial we're going to be working on today. Okay. So now that this is done, we have two working parts which should interlock together. Okay. So our next step is we're going to go ahead and open an assembly. So what we're going to do is typically you'll have, if you don't have a part open, you'll have the option to make an assembly. But right now, since we're open inside of a part, it'll say make assembly from part or from assembly. Okay, so we're going to go ahead and click that button and make sure we open up a assembly. So it should say assemb or assembly 1 at the top. It'll take us a few seconds to load. Yep, you can see it's loading in. It's going to give you this prompt on the left side here to begin assembly. Okay, I'm going to go ahead and start with the pedal, and we may have to remake these assemblies in the future when we do a full build of the entire bike. But for now, this will suffice. Okay, so we have this pedal part now. We're going to go ahead and go back to assembly, insert components, and we're going to go ahead and add the pedal arm as well. Okay. And now we get into the main part of assembly. So now we have the two parts that we want to assemble together. There's a variety of different ways we can do that. So we're going to use the mate tool. So this is very similar to the relation tool, the way that we create relationships between different parts within different lines and different geometries within a part. Mating is how we connect different parts together and align them correctly. So for today, all we're going to be focusing on primarily is standard mates, but I will explain some of the other ones as well. So just to go through all of them briefly, within standard mates, you have coincident. So that will make certain parts touch each other. So for example, I can click a point on the arm and a point on the pedal, and it will lock them together. So for example, that point and this one, and you can see it locks those 2 points together. right? So that's coincident. Parallel, I could select a face of this and a face of the petal, and now it will make sure that they're parallel. So if you look up, the lines there will be parallel. We can select perpendicular. Similarly, I can click here, and it'll make sure those planes are perpendicular. Tangent, similar thing. You can click here, click say a curve like here, and it'll make sure that plane is perpendicular, or sorry, tangential to a part of that curve. Concentric, make sure holes are together, and this is going to be one of the ones that we're using. So we're going to select the cylinder face of our arm and the cylinder face of our shaft, okay? And it's going to make sure that the center axes of these are aligned. So the center, how SolidWorks would define this is it sets the center axes of these cylindrical shafts as the same axes. All right, so I'm going to go ahead and click OK. All right, and you can see now these are aligned. Yeah, it is much better than CATIA. I agree. So yeah, it sets those center axes together. So I can grab this, and you can see that the mate is already there, right? You see, there's a few problems, obviously, that I can pull it through, but you can see that that shaft now moves exactly the way it should. Next thing we're gonna do is we're gonna use the.
Sorry, Jeremy. I don't know if it's just me or your stream is not like working properly on my screen.
Oh, is
It's
anyone
like
else having
loading,
issues?
like a Discord loading. I'm not sure.
I think your internet's just kind of terrible.
Is it my internet or is it Mohammed's?
Ahmed's.
Okay. Well, unfortunately,
Wait,
that
let
I
me
can't fix.
rejoin.
Don't think there's anything that can be done. Sorry, man.
Okay.
Yeah. I'm just gonna finish up with this, and then we'll grab a 5-minute break, and maybe you can take the time then to fix something. But yeah, so I'm gonna take a look at this, and what we're gonna do is we're just gonna mate the face of this shaft to the face of the arm. Okay, and you can see that SolidWorks is already suggesting which mates to use, which is good. In this case, we do want the coincidence one, so we could set these parallel. Just to make sure, but that would actually over-define because we already know that this axis is going to be parallel to that one since they share a common axis, right? But we're going to instead make them coincident, and that's just going to make sure the two planes are in line with each other. So now we can see this mate is working exactly as it should, right? And at this point, this is kind of fully defined. You can see in assemblies, you will still sometimes see underdefined even if something is fully defined. And the reason for that is sometimes, for example, in a real bike, right, these two parts should move independently of each other. Now note, you shouldn't be able to move the pedal. The reason why we can't move the pedal is because the pedal is the base part for the assembly. Okay, that's a very important concept to know, the base part of the assembly. Whenever you're doing, for example, when we do our full assembly of the bike, it's important to note that the base part should be the frame, right? The frame or the seat or some part that is relatively stationary to the bike itself. And that's going to make doing animations and doing static analysis and dynamic analyses of your parts and assemblies much easier because it'll allow you to actually move these parts and detect kind of any problems that come up, right? So we can see that this basically, this spins around. This is exactly how bikes should work. So this is now, as far as we're concerned, fully defined. Okay. So last thing I'm going to do is just show this off with the edges off, and you can see that looks pretty close to what we are going for, right? So if we compare the two of those, can maybe pull this off here. We're looking
Yeah, it
pretty
looked
close,
awesome.
which is good. Okay, so I'm gonna go ahead and let's take a 5-minute break till 7:30. Go ahead and grab some water, try to fix your internet. We'll be back. In the second half, we will be looking at, I guess, the second 40 minutes or so. We'll be looking at mass and material properties, and we will also check out renderings briefly. Okay, I'll see you guys in 5. All right. Getting back into it now. But here I see you asked a couple questions in chat. It's great. Thank you for putting them in text. That makes it much easier for me to take a look through them. So let's go through those first. So first question is, can you show how to make the part that is imported first in an assembly be to float and another item to be fixed instead? To be honest with you, I don't know how to do that off the top of my head. That would be something that probably Google can answer better. My advice is typically make the fixed part the first part you put into an assembly, and then you don't have to deal with that problem. But I'm sure there is a way for you to fix or to change which part is the base part. Take a quick look through. See if there's a button for it, but off the top of my head, I don't know the answer to that. It is a very good question though. Especially if you do a lot of assemblies, that might be a good thing to know. No, I don't see it. So yeah, that would be a good thing to Google, and if you know the answer, maybe post it in the thing. If not, I can take a look at it outside of the tutorial and maybe check that out as well. Second question, can you show how you activated real view graphics? So this is not really the graphics section, but basically just this top button here, the display style we can change. So this is the typical view. You can see the lines, which basically just show as a break in tangency between parts, which is pretty typical for when you're doing CAD. There's a shaded view, which basically just removes that. And so this view basically just allows you to see kind of what your parts are going to look like in a slightly more rendered format than with the lines. There is also a better graphics view, which you can enable with SOLIDWORKS add-ins, which is Photo View 360. So if you click SOLIDWORKS add-ins, Photo View 360, it'll load, it'll take a minute, and then you should see render tools pop up. And you can either do a final render once you're satisfied with your part, or you can do an integrated preview. So for now, I'm just going to do perspective view, but generally you want to do a camera. So a camera will create a fixed view that you can reference that will always have the same perspective on your assembly. Perspective view will basically just update the graphics based on your current view. It's very, very slow, and it is very CPU intensive. So you can see right now my SOLIDWORKS is already frozen, so we'll give it a second to load. Yep, and you can see it starts to render pixel by pixel. It uses an algorithm that it basically loads large chunks and small chunks and smaller and smaller and smaller. You can see it'll slowly kind of fill in the details. I'm just going to go ahead and zoom in a little bit here. It's about there. I'll let that load for a second while I read your next question. Would inserting the pedal image into SOLIDWORKS and tracing it be a good approach? Yep, that would be a pretty decent approach as well. The best approach would be to physically measure the part. So I don't know if the website that we're using, Sketchfab here, actually allows you to download these models, but that's something you could also do is download the model and directly measure it. Or if you had access to the part you were CADing, physically measuring that using, calipers, micrometers, and items like that would probably be the best method of matching that. But yeah, putting the pedal image in, getting the overall shape right, and then dimensioning it based off of the image would also be a very good method as well. Similarly to what we did in the last tutorial. And 4, can you go over how to do mates with limits, like the max angle which this arm could turn? That's a good one. Trying to think how we can implement that in this. We can do it relative to the pedal face. So yeah, we can give that a try. Yeah. This is basically a basic render. So this is something that I think is on the schedule for next week, drawings and renderings. That probably will be about an hour, and we might go into the next lesson as well. But so this is basically the most basic version of a render. So if you're trying to, do something for a school project, for example, like a class project, you don't have a lot of time, this is a very easy way to get a nice view for your front page or whatever, for your CAD model, stuff like that, something you can show off. But it is a little bit rough, like you can see, especially with the pedal. The gradient, for example, on this chamfered edge is really bad. The way you'd want to do this is you doing the final render. I'm not going to go into that now because it's going to take a decent amount of time. Final renders can take between, depending on the quality you're going for, you can get 8K or 10K photos from it. It can take, anywhere from 20 minutes to 7 or 8 hours, depending on, again, the quality, the lighting, and a bunch of different factors. I'll just drop out of integrated preview here just so we can move around more quickly again. One other thing, you should almost always click this button. There's large assembly settings here in the assembly tab. Okay, whenever you click this, you can see it takes out a lot of detail, right? So it takes off a lot of the shaders, it takes off a lot of small details and stuff like that. This model doesn't do too much, but when you're dealing with assemblies with a few hundred or a few thousand parts, large assembly basically allows you to move it around. A lot of the time when you try to move around a large assembly without having the settings on, it takes a lot longer for the parts to move around because it has to calculate all the geometry constantly. So this makes it a lot less intensive on the CPU and helps you work with larger assemblies much easier. Okay, let's take a look at that angle limiter. I haven't actually touched the angle limiter in a while. And I don't know if the geometry we've created here is very good for it, because we don't actually have a very good face on this to use for the angle limit. So let's take a look. Yeah, I don't know if there's a face we can really use on this. We might be able to pull from the pedal arm one of the planes to use. Oops. So this should be our top plane. And then maybe if we do that, we could set a specific angle here if we wanted to, for what the angle, we want the angle to be. But I don't believe this is a limit. The limit I think is an advanced. Oh shoot! I clicked it too many times. Hold on. CPU is not happy. And if we go to advanced, I think. Yeah, so the limit should be here. So you can see there's an outer limit and then an inner limit. So let's say this is 150 degrees, and then we'll set the inner limit as 110, let's say. We can set that. And once we grab the shaft, you can see it's now limited to that range of motion. Okay, does that make sense? I hope so. No problem. I'm going to go ahead and delete that mate just because we do actually want it in this case to rotate around. Okay. Okay, next thing we'll do is we're going to look at mass and materials. Awesome. Okay, so basically what mass does, it is in the evaluate tab here. So we can do this on individual parts, we can do it on our entire assembly, we can do it on sections of a part. There's a lot of different things we can do with the mass tool. The main thing, you click on mass properties here, we get this massive list of information here. So I'm going to go ahead and click just on the pedal arm. Okay, so I'm selecting the pedal arm and I'm just going to recalculate. Okay, and so if you remember, we put carbon fiber as the material. One thing to note is that depending on how your carbon fiber is manufactured, how, especially for composites, how the method of manufacture of your carbon fiber parts or fiberglass parts or anything like that is going to heavily change the mass of the part, which is also going to change its strength properties, its density, all these different things. So Just keep that in mind. Sometimes composites are not filled in. Sometimes they're hollow, especially with 3D prints. Doing mass calculations on 3D prints can be particularly challenging if you don't do it through a slicer, because knowing the final geometry can actually be quite difficult, since the inside of it is largely hollow and you don't always know the exact percentage of which is hollow. But the mass properties tab here gives you a lot of options in what you can learn. So for example, if we look at our drone, we need to know what our maximum takeoff weight of the drone is. We can estimate that by collecting all of the individual parts of the drone, putting them into an assembly, and then what we can do is calculate very simply the total mass of the parts or of the assembly there, and a breakdown of which systems are the heaviest, which ones we need to change, and things like that. This is a tool that we'll use later on in the year once we have more of a comprehensive CAD model of the drone. We'll use this to kind of narrow down which sections of the drone need to be lightened and so on. It calculates the volume. This is very important because it can be incredibly difficult to calculate the volume of complex shapes like this, and SOLIDWORKS gives us a very easy way to do it. It also gives you surface area. Surface area can also be very important, for example, for heat transfer. So if you're making things like radiators, you're working with, I don't know, for example, you're making a cover for a Jetson Nano, or you're making a cover for an Arduino, or for something like that, and you want to know how much surface area you have or how much surface area is open. SOLIDWORKS has these tools, allows you to kind of predict airflow a little bit better. It gives you the center of mass. This is a very, very important tool, especially with control systems. Knowing the exact center of mass of an object is very, very important in performing dynamic system identification. It'll also give you the principal axis of inertia, so your moment of inertia around the center of mass. And yeah, that's the large point of that. What else does it give you? Yeah, I can calculate weld beam mass if you get into that as well. That's pretty useful. There's one more thing I wanted to show on this, which was... I think it's sensors. It's in... Yes, okay. So sensors in the Evaluate tab are tools you can use within your CAD file to alert you to certain problems that you want to keep an eye out for. So for example, if you are doing a lot of work on a CAD model, right, and you want to make sure that the weight of your this arm, for example, never exceeded, 100 grams, let's say. So I know that the mass of this is 96 grams, and so maybe I want to alert if it is greater than 100, right? And so I'm going to click OK on here. And so what this does is it's created a sensor, which I think is up in the tab here somewhere. Yeah, it's in here. So in this little sensors tab, it'll give me an alert if me or anyone else ever changes this part and it causes that to exceed that weight limit, right? So this is a very simple version, but there's quite a few things you can do with it that are very useful. Some of which I don't think I have time to really cover here, but for example, one thing that's very useful about these is if you do it with volume. There's a way for you to actually set a certain volume. So say you wanted to design a water bottle that could contain 100 milliliters. You can set a sensor up so that a certain part of your water bottle will be able to fill 100 milliliters. So for example, when CAD designers in industry are trying to design a water bottle, right? They'll do this process. Well, they'll set up the sensor, and what it'll do is it'll tell them how big the water bottle, how big, for example, they need to scale their water bottle for it to be a 100 milliliter one, a 1 liter bottle, and stuff like that. And then when you go to manufacture that, you'll see that the volume of water you can put in will match up very closely to what you do, and that'll make it significantly easier than you trying to change all the dimensions of your water bottle to match that. It'll kind of do all that for you. I don't really have time to show that because it's kind of a longer process, but if you Google it, that's a very good thing for you to take a look at. Okay. Okay, I'm going to go ahead, so we're a little bit ahead of schedule today. I'm going to talk a little bit about the CSWA and do a practice example. So at this point in time, what we've taught up to here is a large part of what you need for the CSWA, which is a Certified SolidWorks Associate exam. So this is basic exam, covers 240 points, 14 different questions that you need to answer. We'll cover basically all the different things we've done and in quite a lot of detail. So let's see if I can pull up an example question for us to go through. Okay, so let's take a look at this. So, okay, so there's some basic drafting competency questions. So, if this is a test you're interested in doing, this is some of the stuff you'll need to know. So, for example, to create drawing view B, is it necessary to sketch a spline as shown on the drawing? Drawing view A. Okay, I'm going to skip these. We're just going to do a modeling question. Okay, so for example, this part here is one question that you might be given. So you can see based on the modeling that we've done up until this point, this is a very simple extrude. So this is one single extrude. And so we have this drawing with a lot of different dimensions. And this basically is designed to test your understanding of how to use different relationships. So you can see it's a pretty simple geometry. We're going to go ahead and take a look at this real quick and just see all of these different geometries. So grab a sketch. Sorry, need to open a new part. Actually, before we do that, sorry, let's save this properly. So we're going to follow that same naming convention that I mentioned before. So now we have to remember we're now in Assemblies. Save as. We're going to make sure we do 0, 0, dash. We're going to do, call this main assembly. And we're going to add to this as we go. Okay. Main assembly. And so now this is now done. We're going to go ahead and create a new part. So there's a bunch of different ways you can go about doing this part, but I'm just going to draw some lines to get started. We'll use this corner here as our reference, like as our origin. I'm just going to do this kind of left side here, and we're just going to kind of truncate it. And then we're going to call it early for this week. And hopefully, if you guys are interested in this exam, you should have enough information that you're able to do it. If not, then no worries. Okay, so just to add some dimensions here, we know that the distance from here to here is going to be 32. You can also make sure you check the unit system. So you see this is in millimeters. Okay, we know that this distance is 7. We know this distance is 7. Okay, we know this distance is 14. And it'll always give you exactly enough dimensions to make sure that your part is fully defined. We know that the angle here is 10 degrees. I know the angle here is 45 degrees. I'm I'm going to force this just because I cut that. I'll set this to, let's say, 25, just to force that. What other dimensions are we missing? We're missing, let's see. There we go. So see, I'm just using that that method that I always use. Click on the corners and pull it around, and it'll help you find which sections of your drawing are underdefined. So this last section here is the last thing. So we can see that's also 45. I'm just going to go ahead and fill that in as well. And there's your 45. We should be fully defined now, which we are. Okay. And then you just go about extruding that to a certain level. Okay, and that would be your part. You scroll down on this side, you typically have a few questions. So for example, your first question would be, you have to enter a material of 1020 steel with this density, which you would have to force by entering the material settings. So we would open material, right, ANSI 1020 steel, right? We're going to make sure the mass density is correct. It looks like it's the same, just in a different unit, which is okay. We're going to apply and close. Now, it's going to ask you what's the overall mass of the part. So if we go to evaluate mass properties, we'll be able to see what the mass is. Now, because I extruded this, randomly and I didn't finish the part, the mass won't match. But if you take the time to do the part as in the drawing, you should get one of these three numbers. If you don't get one of those three numbers, you've made a mistake somewhere. So make sure you take the time to look at those. There's also a 1% plus or minus error. So if that's something that you're interested in taking, just keep that in mind. And that's pretty much it. Most of the questions on the CSWA are very basic. There is a few questions related to mating. So for example, the question that Bahir had asked previously, there's some angle limitations here that are put in place between these flat faces. And yeah, that's about it for the CSWA. So if that's something you're interested in taking, you can go to the SolidWorks website, and the information should be available there. Okay, that'll be it for this week. Next week, as I mentioned, we'll be going over drawings, renderings in a little bit more detail, specifically designed for our team, but with a little bit of information for general. We're also going to hop up into the CSWP level, tackling holes, equations, shell, rib, interference testing, tolerancing, suppression and collision detection, and we'll probably start working on that project that I mentioned as well. So we'll start working on the practical aspect of the team as well. Okay, thanks everyone for coming, and we'll call it there.